Hello everyone. Welcome back to the session on your process synchronization. I think you people have gone through a few videos related to your process synchronization, which I have uploaded it, and you might have seen what exactly this whole process is all about, right? So till now, I think you people might have understood why we are using this particular process synchronization mechanism. Sorry. So here in this particular session, we will be discussing the last part of your process synchronization. Okay. So the part one, we are going to end today with this particular session. So till now, whatever the discussion we have gone through it, that is related to your how we can synchronize the processes. Since we know that in our system, multiple processes are executing simultaneously, right? Multiple processes are executing simultaneously. So definitely these processes might be accessing some resources, right? There are limited resources. Since we are limited in size, okay, limited in resources, we have to make sure that these whatever the resources we have within that only all the processes, whatever the task of the process is there, that we have to fulfill it. That is the main thing. So for that purpose, what we are actually going to do is process synchronization. So making sure that with a limited number of resources, all the requirements of a particular process are getting done. That is what we are actually performing in this particular unit, right? That is what we call process synchronization. Means without any conflict between two different processes, they are accessing the same resource. They're trying to access the same resource. Using that resource, they are performing the operation and completing whatever the task is assigned to that respective process. That is what we are doing it. Okay. Or else what will happen if there are multiple processes are executing, definitely there will be a collision. Collision is with respect to the resource. Since we are limited in resource, we may not be able to provide the resource to each and everyone. So there the problem actually comes up. That is the main thing. So to overcome that only we are performing this particular process synchronization mechanism. So till now we have discussed the different solutions. First we discussed about something called as hardware solution. So in the previous slides or the previous videos, we have discussed about hardware solutions. So using hardware, how we can provide this process synchronization. Then we went for a software-based solution. That also we have gone through it. So I think if I'm not wrong, this one we have given a name, right? Peterson solution. Okay, even though it has certain limitations, still we actually discussed this particular solution, right? Peterson solution, and it's purely a software-based solution, and it can be implemented when there are only two processes. So when there are only two processes, then we can implement it. But the best part is the way this person has expressed the solution that can be implemented for designing our own algorithms for process synchronization mechanism. That's the reason we have actually discussed about software solution. And after that, we have discussed something very important, something called as semaphores. Yes, this is the one we using which we have actually provided solutions to many of the problems related to this particular synchronization. So we have discussed in using semaphores, we have provided solution to something called reader-writer problem, right? So after that, we discussed about something called as dining philosopher problem, very important, what we call part related to your synchronization, dining philosophers. And after that, we also discussed about something called as a producer by consumer problem. So all these we have seen the solution using semaphore. Basically, I think you people know by the time now what do you mean by semaphore? This is nothing but it's an integer variable. Semaphore is an integer variable. Everyone represents with their own way. So this guy has represented, this author has represented semaphore with a variable yes. Okay, the way we people declare in a C programming or in any programming, the variables we declare int a comma b comma c. Same way here, the semaphore is the integer variable. Okay, like this. But apart from this initialization, it can be accessed only with the help of two different operations. Those are very familiar operations what we have using wait and signal. And in this we have provided solutions to this particular reader-writer problem, dining philosopher and producer consumer problem. So those who haven't have an idea related to this particular thing, please watch the previous video so that you can get a clear idea about this particular semaphore. Now today we will be discussing about, this is related to the previous slides, whatever we have discussed in the previous videos. Now in this session we'll try to wind it up. So as I stated, we discussed about the background related to your process synchronization. So in this, the very famous problem what we have is critical section problem, making sure multiple processes are not fighting for the same resource simultaneously. Okay, at a time giving them one by one and getting their task executed. That is what critical section problem is. Then solution, that is nothing but your Peterson solution. Followed with that, we have seen something called as hardware synchronization. That is nothing but hardware related issue, solutions related to your process synchronization. I think in this we discussed about test and set function. This is very important function. And after that, we have discussed about swap, right? Swap function. So these two are some of the one which are related to your synchronization hardware. And after that, we also discussed about mutex lock. And then finally, the important part, the semaphores. And related to this, we discussed about something called as classical problems on synchronization. So here we discussed about something like, reader-writer problem, reader-writer problem. Then we discussed about something called as dining philosopher problem. And if I'm not wrong, after this we discussed about something called as producer by consumer problem. Okay. Now today, in this particular session, we will be actually trying to complete the last part of your part one, process synchronization, that is monitors. Means this is also one type of solution for your process synchronization, same as that of semaphores. So using semaphores, we have tried to solve the problem. Same way using monitors, this is another method using which we can try to overcome this particular process synchronization problem, whatever the problem we are having here. So that we can overcome using monitors also, that we are going to discuss it. Not only that, even we are going to provide a solution for this particular dining philosopher problem. Okay, so we are going to provide a solution to this particular dining philosopher problem using monitors. Well, let's get into it. So first we'll discuss some brief introduction related to monitors. Okay. Now basically we know that semaphores has already provided a solution to overcome this particular problem related to your what we call process synchronization. But the thing here is that it is nothing but it is an integer variable s, which can be accessed only with the help of two operations, wait and signal. Well, this is what we have actually discussed. Well, basically now using semaphores also still some problems do exist. Okay, some problems definitely exist, okay, even when we are applying this particular semaphore, and that will lead us to something called as timing errors. Even though we are applying that, we will be coming across some timing errors which are very difficult to detect. Okay, even it is providing a solution. Semaphores provides a solution to the critical section problem and process synchronization. But even if this particular semaphores we are implementing, there are times that if the programmer is not using this particular semaphore perfectly, okay, not utilizing it perfectly, definitely there might be some kind of errors. That is what we call it as timing errors. And these errors are very, very difficult to detect. We cannot detect it easily. Yeah, you will not, it's something like, you people will be reviewing your program, whatever you written, that will be represented as correct. But you're not, but the output you might not be getting perfectly. There might be some kind of errors. Why that errors are actually coming up is nothing but some same sequences. Now, the best example for this is the first beginning of this particular unit. We discussed a problem related to your producer by consumer related to a variable called as counter. If you don't remember this, please watch my first video of your process synchronization. You will get the idea. So here we have seen that how this particular variable is getting two different values, 4 and 5, for a same variable called as counters. So that problem is what we call it as timing error. And until and unless we are executing it using a pen and a paper, we will not be able to identify where exactly the program or the logic is going wrong. And moreover, these kind of problems will not come regularly. It's not that frequently it will come. Very less frequently it is going to come up. That's the reason I have given the example here. You can see here the example what is provided, counter variable problem and producer by consumer. This we have actually covered in the first video of this particular synchronization. You can go through it. Okay. So that is what he's saying. Now, apart from that, we may be having other problems related to something called as even we know when we are using semaphores. Okay, like for to express or illustrate those particular problems, we will be considering a semaphore solution. I'm going to take a consider okay a semaphore solution Okay, and that is related to critical section problem. So we have a problem here, critical section problem. I'm going to take a semaphore, and you people know that semaphore s is an integer variable, right? Now here, in case of this particular variable, I am calling that variable with the name called as mutex. Okay, all the processes will be sharing this particular semaphore called as mutex, and initially the value of mutex is initialized to 1 because it is empty, it means it is free. No one has access it. Whenever someone is accessing this particular semaphore, then the value becomes 0, indicating that someone is already present in the critical section and he is executing. So no other process should be allowed to enter into critical section. That is what I think we call it as mutual exclusion. So we are applying that particular mutual exclusion. So here, whenever a process want to enter into the critical section, we know that it has to execute two operations or two functions. The first one, whenever the process want to enter into the critical section, he should execute wait operation, wait of mutex. And once he completes executing in the critical section, when he is coming out, then he should execute signal of mutex, right? So whenever these two are executed perfectly, then only a process will be, only one process at a time will be present in the critical section, performing the operation and coming out. But if this sequence is not observed properly, then definitely several different problems can come up. So what are the problems that we are going to come across? Let us take this particular slide and understand it. Now, first thing, suppose that a process interchanges the order in which the wait and the signal operations on a semaphore are executed. Means basically what did I say now? What is the process? Means whenever a process want to enter into the critical section, what he has to do, he should execute wait of mutex, right? And when he's executing that, then he enters into the critical section. If the mutex value is 1, that this will become 0 and then this will be assigned to the process, he will enter into critical section. Once he completes the task here, he will be simply calling as signal and then mutex. Now in this case, what is saying is that suppose a process interchanges the order, means in place of wait, the process you people are writing as signal of mutex, and in place of signal you people are writing wait of mutex. Now what will happen? Can anyone can guess what exactly is going to happen here? Let us suppose the process P1 want to enter into critical section. He is calling signal, and when we call signal, when the process comes out of a critical section, so in the beginning if he is indicating that other processes that I am coming out. Then what this process is going to do, he will also try to enter into the critical section. So simultaneously P1 and P2 are in the critical section. So the very first law, what we have discussed about critical section problem is mutual exclusion, right? So what do you mean by mutual exclusion? At a time, only one of the process can enter into the critical section and execute that particular task. Now what is happening? So two processes critical section. So definitely the mutual exclusion rule is violated. So we cannot get a solution to the critical section problem. That is what he is explaining in this particular scenario. So let me erase it and show you the program so that it becomes easy for you. Here it is. You can see here, actually what is the process we should write here? Something, basically it should be like, wait of mutex. Then we will be entering into critical section, then signal of mutex. So in case there is a change in, so signal is calling. So what happens? Two processes, multiple processes might be present in the critical section at the same time. So that results in a mutual exclusion violation, right? So we have three requirements that need to be satisfied. Then only we can say it is a perfect solution to the critical section problem. What is that? Mutual exclusion, bound waiting, progress. So the very first condition is getting violated because of this particular scenario. So automatically it's going to lead to not a proper solution to the critical section problem. And the second assumption what we are going to see is, suppose a process replaces signal with mutex, something like this. Now, can anyone tell me what is going to happen here now? Wait of mutex, critical section, wait of mutex. Now, okay, first step is correct. Whenever a process want to enter into the critical section, he will call wait of mutex. Then he will enter into the critical section. He is performing the operation. So when he is completed executing it, he has to give signal. Instead of signal, he is giving wait. Then what is doing? He is waiting for, means what is exactly doing? He is waiting for the critical section to be free. But who is actually holding that critical section? The same process who has executed wait. Now what does that mean? This process is having the key and he is waiting some other process to give that key so that he can open that particular critical section. Is it really possible? Something like, this person is having, this particular process is having a key of a door which you want to open it up and is waiting for someone else who is having the key to give that particular key to him. Means by himself he is asked, saying that he has to give it to its own way. Means himself he has to give, but that's highly impossible. Na? You can give a key to someone else, but to yourself, can you give it by automatically by your own way? Well, it's highly impossible. So what happens here? A deadlock arises because a person can never give himself a key. Okay, someone else only has to give it. By himself, that person can take a key, but he cannot give to himself that particular key. So that will definitely lead to a deadlock situation. Why? He is having a key and is waiting for himself to give the key. It's highly impossible. So he will be starving. Deadlock arises and that leads to a starvation of that particular process and other starvation of other processes because he is having the key, he is waiting for the key, he is not releasing it. Other processes will be suffering there, waiting for the turn, and they will never get a turn because this person has having the key and he is waiting for a getting a key for entering into a critical section. It's highly impossible thing. Okay, so this is what he means to say in this one. So these are the two scenarios. So if any of this particular scenario takes place when we are writing a program as a programmer, so definitely problems definitely arises. Yeah, definitely there will be problems and it's highly typical to overcome this particular problems. So in order to overcome that only, okay, so that is what it's saying here, either mutual exclusion is violated or the deadlock will occur. So in the first scenario, this one, you have seen that mutual exclusion is getting violated. In the second scenario, what we have discussed here, a deadlock is actually arising or the starvation is going to lead us. So to overcome that only, we have introduced this particular concept called as monitors. Yeah. So monitors have come into picture. Now, before discussing about monitors, I want to just flash some light related to something called as ADT, which you people are already familiar with. I think you people know what do you mean by ADT. You people have discussed this in your data structures, right? Abstract data type. So I think you people know what do you mean by abstract data type here. Okay, so this is nothing but it is the one which encapsulates. So it actually encapsulates data, okay, along with some set of functions. So this is there is a data, there are set of functions which we have placed in a block. That is what we call it as encapsulation. And this set of functions can perform operations based on the data whatever is specified within that particular block. And not anyone can access this particular block. Only who have the rights to access this particular block, only they can try to perform operation on this particular block. Okay, so these set of functions, whatever we are defining here, they can you make use of the data that is declared within this particular block to perform the operation. Okay, so indirectly what it means to say the data is local, not what we call global. Okay, whatever the data we have, the data is not global, it is purely local, and only the local functions can try to access the data and perform the operation. When I will show you the structure, a clear idea of what exactly we are implementing. Okay, so here the monitors type has come into picture. And the best part of this particular monitors type is the thing is here you don't have to worry about making sure that mutual exclusion is taking place or not. Mutual exclusion is taking place or not, you don't have to worry about it. Why? Because see, the structure of this particular ADT is designed in such a way that automatically at a time only one function can execute. There might be multiple functions, some set of functions are present in the block, but at a time only one particular function can be executed. So that is what we want, mutual exclusion. At a time only one process should execute. You assume these functions as a process. So set of processes are there, at a time only one process can execute. So by default, the mutual exclusion is satisfied. You don't have to write a separate code or something like that to make sure that mutual exclusion is satisfied or not. Something in semaphores, we use it like, wait of mutex, execution, then critical section, then we had something called as signal of mutex. These things are not required now. Why? Because we will be declaring some functions like this, and this will, there is function 1, function 2, function 3, so on. Now at a time, whenever you're calling, only this particular function will execute. If this function is not executing, either this one or this one will execute. At a time, only one of the function is going to execute. Okay, let me show you the structure of it so that you can get a clear idea. You people already used it in your programming language. Yeah, this is the structure. The monitor, you can see here the structure here, monitor name. So here we, this is what I was talking about, shared variable declaration. So this is your data. Whatever the local data you people are discussing. So here we have function 1. So you're performing some operation here. Function 2, performing some operation. Function n, performing. So on up to n. Then we have something called as initialization code. So this is the initial code, whatever we declare it, that we are going. So if you see here, excuse me. So if you see here in this particular scenario, so at a time if you see either P1 process, why I have written P1 here is nothing but this is you assume in a format of a process 1, process 2, process 3. So one of the process n. So at a time only one of the function will be executed here means what does that mean? Either P1 will be executing or P2 will be executing or Pn will be executing. But simultaneously all the three will not be executing the operation. That is what he's saying in this particular thing. So that is what we want also, I think, if I'm not wrong. At a time only we want one process to execute in the critical section. So definitely mutual exclusion is satisfied here. We don't require now something called as wait and signal operations. That operations we don't require in this particular scenario. Because the body or the structure of your monitors is itself designed in such a way that it satisfies mutual exclusion. So this is what he is, whatever we have discussed till now, that is what he's saying in this particular scenario. I hope it's very clear here till here. But here, basically what he's saying is whatever the data structure we are providing here, I mean, okay, let me erase it. Now, whatever the data structures you people are seeing here, function 1, this one, okay, individually it will be executing one at a time, oh, that's fine. But whatever is defined here, that is not sufficient. Sufficient in the sense that there is a possibility that some errors may take place when we are implementing some complex kind of situations. To overcome that, only what these people have did is they actually started defining conditional variables. Like in semaphores, we have a variable called S. This is initialized to 1, right? Same way here also, these people are actually defining monitors condition variables. Okay, so two variables they are declaring x comma y. So the x is one variable, y is another variable. That I'll show you in the preview in the next slide here. The two variables of type conditions will be defined in this by the programmers, condition x and y. And only same in the like the way semaphores we can implement only with the help of two operations. Here also only with the help of two operations we can invoke these conditional variables. What are those? X and y. So that is x dot wait, x dot signal. Okay. So using these two operations only we can access this particular variables. Like in semaphores S, we can access using wait and signal. Same way here also, the conditional variable x and y can be accessed only with the help of two different variable, I mean operations, wait and signal. So what is the meaning with respect to x dot wait here is that a process, whoever invokes this particular x dot wait, that particular process will be suspended until x dot signal is initiated by some other process. Okay, let us suppose P1 is there, P2 is there. P1 is actually calling x dot wait. He want to enter into critical section. As soon as he is executing this, this particular process will be suspended. Until what time? Until another process P2, who is actually working in the critical section, when he is coming out, he should give x dot signal. Remember, if the process P2 is giving y dot signal, then this will not be waken up. Only x, the variable is most important here. When he is giving x dot signal, then this particular process will be woke. It will awake up. The system will make it awake that okay, critical section is free, now you can enter into the critical section. The next one, x dot signal. Okay, so I think it's clear now. If it is giving y dot signal, this process will not be resumed. Another process might be there who is with respect to the variable y. This is actually this might have executed y. So whenever it is giving y dot signal, this process will be waken up, saying that the critical section is free, you can enter into the critical section, not this particular process, because he is with respect to the condition x. not with condition Y. So in the extort signal, it resumes one process that invokes extort wait. Okay, so it resumes one process means already this process is suspended, right? Extort wait. Whenever this process is executed extort wait, it is suspended now. So it's waiting for extort signal. Whenever a process gives extort signal, immediately this it will awake this particular process P1. So whenever a process is giving extort signal, the process which is suspended due to x dot wait will be awakened. And remember, only one process at a time, not multiple processes. So that is what he is saying. But if in case extra wait, okay, here there is a small thing which I wanted to clarify here is that here if this particular process is no process suspended, whenever the signal operation is executed, na, I mean extra signal is operated, and if there is no process waiting for, I mean in a suspended mode, then this signal operation will not have any effect. For example, P1, P2, he has called y dot wait. P2 is there, he called x dot signal. Now what will happen? X dot signal means with respect to x condition, whichever the process is there, that we can work up. But actually we have only one process here, that is with respect to y condition, not x. So even though this particular process is executing x dot signal, it will have no effect. It will have no effect as if it is not executed because there is no process with the condition x that is in a suspended state. If another process is calling y signal, then this particular suspended process will be resumed and he will be awake. He will wake up and he will start performing operation. Now, by entering into critical section. This is the way how it is going to work in this particular scenario. I hope it's very clear here till here. Okay, so this is what he's going to do. But there is a possibility that let us suppose that if a process P is there, okay, process P, okay, I'll explain the example. If there is a process P which has executed extort signal, means there is some problem here. What is the problem? P is executing extort signal and we have another process Q which is in a suspended state. This is in a suspended state. Now here, whenever this process is executing extort signal, he is still in the critical section only. Okay, so he means, I mean to say that he is still executing. He completed the task, but he is executing extort signal. But when he is executing extort signal, this particular process is woke up. It will wake up. Now he will also enter into the critical section, start performing. But he did not completely come out of that particular critical section. So what happened? Both of them simultaneously present in the critical section. P and Q are both simultaneously present in the critical section for execution. Remember, there is a small difference between semaphores and this. Whenever a process P1 is calling extort signal, immediately whatever the process is in a suspended state, it will enter, it will woke up and enter into critical section. But he is still coming out of the critical section. He just gave an alarm that I have completed my work and I am about to move. But he did not come out of it. He has some work to be done. Okay, but immediately this person, this fellow is coming and entering into it. So what happened? Both of them are simultaneously present in this particular critical section. So definitely there will be a problem now. What is the problem? Two at the same time. So to overcome this particular, they have come up with two different methodologies. So that is what whatever. So they have given two options, signal and wait and signal and continue. So what do you mean by signal and wait here is that P will be calling X dot signal and he will wait or suspend himself until Q wakes up, enter into the critical section, performs the work and goes out. Okay, till then this particular signal, he will give extra signal and he will wait for this particular process to resume, perform the operation critical section and move out. Okay, so he will be in a suspended state. He will come out of the critical section. Or else the second option is execute, but he will continue executing it. Okay, P will actually call extra signal and he will continue his work. Whereas what about the Q? Q will wait. Q has been woken up. Q has woken up now, but he will wait until the process P completes entire work and he comes out. Once he is coming out, then Q can enter into the critical section. So if I ask you among these two, which one is better? Can anyone tell me which one is better? Signal and wait is better or signal and continue is better? Well, most of them will suggest for the B1, signal and continue. Why? Because see, already process is P1 is executing. He has given X dot signal. He is already executing in the critical section. Why should we make this fellow to suspend himself for P2 to come and perform the operation? Isn't it? So we will allow, so signal, he will give the signal, I am going out, but he will continue performing the operation, complete the entire task, and then he will come out. Then the process P2 can enter into the critical section. So this is nothing but Q, this is your P. So you can give any variables, okay, don't get confused. So these are the two options provided for overcoming this particular problem. Okay, I hope it's very clear with this. So mostly everyone follows this, but still, even I have given the second option, most of them, but some people give this option also. Why not this one? This is also actually correct. So in this case, to overcome this, what they have decided is that whenever a particular process executes a so the final solution, what they came up is, whenever a process executes a signal operation, it will immediately leave the monitor. It will immediately leave the monitor. I think you people know what is a monitor. I have shown you on the previous slide, that diagram. Okay. So whenever a particular process is leaving, he is giving a signal operation means first he has to complete the entire task, then he has to give the signal operation, and then he will be coming out of that particular monitor immediately. Then Q can enter into it and perform the operation. So at a time only one process is entering into critical section. Okay, please make clear. So even though the solutions are provided, some people went with the option of something called people went with the option of something called A, some people went with the option of B. So how to overcome this problem? They came with that particular solution. What is the solution? If a particular process P is indicating X dot signal operation, then he should immediately after giving it, he should not wait now. As soon as he is giving the signal, he should not wait. Immediately he should leave the monitor. I hope it's very clear. So then Q will enter into critical section and perform the operation. Okay. So I hope it's very clear till here. That is what we do have here. Now after this, I am going to provide you a diagrammatic view. This is the diagrammatic view of your monitors, whatever we have seen. So if you see here, there we had something called variable declaration. So in this scenario, we have shared variables here. Okay, and then we have function 1, P1, function P2, and so on up to function Pn. So that is what represented. So operations are nothing but your functions. And then the bottom I had initialization code. Now this is what the initialization code. And here we have entry queue in the sense that data will be shared by different processes. That is what represented here. This is the normal methodology what we have given. But later on we said that this cannot be perfectly implemented for every complex problem. So we use the condition variables, right? Condition variable x comma y, and they access only help of x dot signal. Same way y dot wait based upon the condition y dot signal. So that's what is represented in this particular data. So we'll be having a separate data for x condition and separate data for y. We have a set of operations here, and then finally the initialization code. Now using this, we are going to provide you a solution for a dining philosopher problem. Okay, I think you people are familiar with dining philosopher problem that we have already discussed in semaphores. So I'm not going to explain much about that. We'll simply dive into the solution related to your dining philosopher problem. So let me give a small introduction here. So we have 5 philosophers here. One, two, three, four, 5. There is a round table here. There is a rice bowl. Here they are having a bowls for eating and 5 chopsticks. Okay. Now, so the philosopher, what he does, he only keeps on thinking. Whenever he feels hungry, he will start eating the rice. But whenever he's eating the rice, what we said, he should have both the chopsticks in his hands. Then only he can eat it. Okay. With the help of single chopstick, he can't eat. Both the chopsticks should be available, which is onto his left hand and which is onto your right hand. Then only he can start eating and perform the operation. So we have seen a solution using semaphores. If you don't remember it, please watch my previous video so that you can get a clear idea. Okay, how we have provided solution using semaphores. In this scenario, we are going to provide you a solution using something called as monitors, and this is much more easier when compared to your semaphores. So what are the data structures we basically going to use here is we are going to use enumeration here. I think you people are familiar with enumeration since DS data structures is completed. I expect that you people know what is the task of this enumeration. So here we have actually classified the philosophers into three different properties. One, thinking, hungry, eating. So this means that five philosophers, whatever we have, that may be in any one of the following conditions. Either they might be thinking, or they might be hungry, or they are eating. So any three, one of the conditions they might be having. And apart from that, we have something called state of five. I think you people know what is this five. This is nothing but your chopsticks. We have only five chopsticks. Okay. Now, philosopher I can be set the variable. Okay, let me erase it. So we see here, we can set a particular philosopher I. Okay, I is nothing but representing a philosopher. Five philosophers are there. So I equal to 1 means first philosopher. I equal to 2, second philosopher, 3, 4, 5. So whenever we are setting state of I equal to eating, this is state of, I mean, suppose I value is 1. So what is the state of the first philosopher is eating. When we can set this particular variable, when his two neighbors are not eating. Yeah, only if their two neighbors are not eating. Suppose if you take, let me take 1, 2, 3, 4, 5. Let us take the philosopher 1. First philosopher I'm taking. When he can start eating, when he is having both the chopsticks. Chopstick which is present on the left means with respect to this particular philosopher 2 and with respect to the philosopher 5. If these both people are not eating, then only this philosopher 1 can start eating. For that we have written this. Okay, I will show you. What is the philosopher we have selected? 1, right? I am talking about philosopher 1. So I value is 1. Now see here. I value is 1 means state of 1 plus 4% 5 is not equal to eating, and state of 1 plus 1% 5 is not equal to eating. Means second philosopher should not eat fifth. Now, are we getting it or not? You please see here. 4 plus 1 is 5. Okay. Fourth philosopher, now fifth philosopher. Okay, fine, fine, fine. 1. Okay. So here, 5, I mean, 1 plus 4, 5. So 5% 5. So what is the output you are going to get? 0. 1 plus 2% 5 is right. Okay, there is a small mistake here. I think we need to consider this one as fifth philosopher. You can consider it as fifth philosopher, not first one. Okay, I will tell you how even one also we can get it up, but for that we need to write separately code because one means again there's a problem coming. So here if you take the fifth philosopher, okay, I want to take this particular fifth philosopher. So we have first philosopher and 4. So 5 plus 4, 9. 9% 5. What is the output you are going to get? 4. Means this particular philosopher. I am considering this. He wants to eat. So I am considering this the fourth philosopher. Same way 5 plus 1 equal to 6% 5. So 1. So fourth philosopher and one philosopher is not eating here, then only you're going to get. Okay, let me explain it once again so that you can get a clear idea here. I am considering philosopher 5. I want to see that 1, 2, 3, 4, 5. This person has to eat. So I want to set the state of that particular person as eating. When I can do that? Only when the philosopher 1 and 4 are not eating. So how we can get? This is the state what he has given. See here, I plus 1. So I is 5. 5 plus 4% 5. So 9% 5, how much you're going to get? So it's a modulus, reminder. So 5 1 5. So 5, 9, 5. So what is the output you are getting? 4. So if the fourth philosopher is not equal to eating, and what is the next one? Philosopher 1. So that you are going to get here. See, 5 plus 1% 5. So 6% 5. What is the output you are going to get? 5 1 is 5, 1. So 1. So not equal to eating. When this 4 and 1 are not eating, then only we can set the state of fifth philosopher as eating. That is what he means to say. This is a simple code what we are going to use in this particular scenario. Now this is the whole diagram related to it. You can see it. You can see this is the structure we have used. Monitor, dining philosopher. So we are using enumeration data structure, thinking, hungry, eating, state of five chopsticks. Condition self. So self condition we need to know now whether we are in a thinking state, whether we are in a hungry state, whether we are in a eating state. So whenever a process want to eat, he has to perform a method called as pickup. Two methods we are using. He has to pick up the chopstick and he has to put down the chopsticks. But before picking and before putting down, we need to check the condition, whether the chopstick is available or not. That is what we are applying here. This is the method for that. Test. Initialization code you might have understood for int I equal to. So 5 philosophers we have 0 to 5, I plus plus less than 5 years. So 0 to 4 we are representing here. If you don't want to represent in this way, you can simply start 1, I equal to 1, I less than equal to so 1 to 5 on you how you're writing. I have considered 0 to 4 I for representing. Now state of I equal to. So initially all the 5 philosophers are in a thinking state. This is my initialization. Now whenever a particular process want to perform a pickup, I mean eat, okay, he is feeling hungry, he want to eat it up, he should actually execute first thing is dining philosopher pickup. So this is a monitor. Here you can see dining philosopher. Pickup of I, that particular process. Let us suppose philosopher 5. He comes up. Now here when he is coming up, void pickup will set the state of it. So in int 5 means philosopher 5. State of 5 is equal to hungry we are setting. Means that particular philosopher is hungry now. But before he starts eating up, we need to see whether the chopsticks are available or not. That's why we are calling test of 5. And this will be transmitted. I mean, the control will be transmitted from test of 5 to void test of int 5. And initially I told you 5 plus 4, 9%. So fifth philosopher means first philosopher, fourth philosopher. If they are not equal to eating and the state of that particular philosopher 5 is hungry, then we can set the state of I chop available. He has lifted it. He has started eating. Once he performs complete performing means completed executing or eating, he has to signal the other philosophers, that is 4 and 1, that I have completed eating. For that he is giving a signal. Self of 5 dot signal means he is giving a signal to the nearby neighbors that I have completed eating. Same way. After that what is going to call void put down. He has completed eating, put down. So when he's putting it down, what he has to do? Again, he should start thinking. The state of that particular philosopher 5 is set to thinking now. Same way test of I plus 4% 5. So this is nothing but we are thinking means whether the chopstick is present or not with respect to other processes. That is 1 and 4 that we are testing here. Okay. I hope it's very clear till now. You people might have understood. It's very, very easy concept. Let me explain it one more time. Whenever one particular philosopher wanted to access the information, let us suppose philosopher 5, first he should execute pickup 5. So I value is 5. So he will come up here int 5. So he is feeling hungry. That's the reason he want to pick it up. So we will set the state. Initially he is in thinking state. We converted that state, means state of 5 equal to hungry. He is feeling hungry. But that doesn't mean he will be given the chopsticks to eat. We should find out whether the chopsticks are available or not. And that is what we are doing. Test. And that test will transmit here. And here we'll find whether 4, the neighbor 4 and 1 are, I mean this is 5 and this one is 1. Whether the nearby neighbor 1 and 4 are not eating and the state of that particular process 5 is set to hungry, then he can start eating. Once he completes eating, he will give the signal. Again from here the control goes to here. Now if state of I is not equal to eating, then what we need to do, self dot I wait. In case this condition fails, test when someone is already having it, then he is not in a eating state. So what we are doing, we are making that process to wait until either the 4 or the 1 is leaving the chopstick. Both of them have to leave the chopstick. Then only he can access it. That is what we are doing. Once this process is completed, he is getting a chance to eat. After eating, what he has to do, he has to put down. And when he is putting his chopsticks down, again he should start thinking. That's why we are changing the state of that particular process. State of 5 equal to thinking. Then after that we have test of I plus 4% 5. Again means we are making sure the other processes what we have, they are not in a means whether they are holding it or not, that we are seeing it. and then we are putting that particular chopstick down. This is the way the whole scenario works. Okay, it's very, very easy. I want you people to work on this. And if you get any doubts, you can anytime ping me up so that I can clarify your doubts. But just very easy. Just work on it. You will easily come to know, and it's very interesting too when you're working on this particular problem. And the last but not the least is how we can implement monitors. How we can implement monitors using semaphores. Okay, semaphores is S. So we use two operations, wait, signal, and we perform the operation, and that's what implemented here. So we will be implementing this monitors concept using semaphore. So basically we will be using a semaphore called as mutex. Initially it is initialized to 1, and any process which want to enter into critical section using monitors, they should execute first wait of mutex, that we know. So here, to enter into the monitor, the process must execute wait of mutex. And whenever it is coming out of the monitors, it should actually execute signal of mutex. Then only it has to come up. Apart from that, we are going to use another mutex, I mean semaphore. We call it as next. This is initialized to 0. See, two semaphores we are using here. One is something called as mutex, which is initialized to 1, and another is next, which is initialized to 0. And we have next count also. Now, why we are using this variable next count to determine? See, we said that in monitors, whenever a process is calling x dot signal, now he will be suspended now. Right? No, sorry, x dot wait. Now that particular process will be suspended. Then whenever someone is giving x dot signal, then that particular process will wake up. So to determine how many processes are suspended due to this, that we are going to determine using this particular next underscore count. And for that we have given the diagram here. This is what the whole scenario what we have here. We can see it. It's a simple thing. You people can go through it. So initially what is saying, wait of mutex whenever process enters into critical, means monitors whenever a process want to enter, first wait of mutex. If it is available, critical section, that is nothing but your monitor. Body of function is nothing but, we have seen now monitor, function 1, function 2, so on. So that is talking about body of function. So if the next count is greater than 0, then signal, means if there is some processes which are suspended due to this wait operation, then you can give a signal to wake them up. Else signal mutex. Mutex means the next process we are giving it. Here already existing process which is in a suspended state, that we are giving a signal to wake up. In case no process is in a suspended state, when it is calling x dot wait, then we will signal another process to enter into the critical section. Okay, we will indicate then that I am coming out. Anyone is there, you can enter into critical section. Same way is using with respect to your count as well as another one. Okay, these are the two things you have. If people can just go through it, it's very easy. X count plus plus for incrementing. If any process is actually there which is calling x dot wait, so the counter has to increment the x dot count. And based on that, this particular process is actually getting executed, and same way this particular thing is getting executed. This is for removing it. We're decrementing the count. This is for incrementing the count. That for that purpose, we are actually using these two scenarios. Now with this, we actually completed your monitors concept and the first part of your process synchronization. In the next session, we will be discussing about something called as the very most important topic called as deadlock. And it's a very important topic, very interesting topic, and we have some problems related to it to work on. So I expect you people to please complete the part 1 of this particular entire session. Whatever the videos I have represented, please go through it, understand the concept properly, and based on that, you people can work on it. These all the topics what we have discussed in this particular scenario are very, very important with respect to your exam point of view as per your gate point of view. And after this, in the next session, we'll discuss about deadlocks. Thank you. Thank you for watching. If you like my video, please do like and share. Thank you.